Hi, my name is Jang Cho. I'm a PhD student at UT Austin. I'll be presenting our paper PiCIE, Unsupervised Semantic Segmentation using Invariance and Equivariance in Clustering. This work was done with Utkarsh, Kavita, Bala, and Bharath Hariharan from Cornell University. Unsupervised learning via clustering is now popular, but is still limited to images that depict a single dominant object category. However, real-world images typically involve cluttered scenes with lots of visual concepts. It is impossible to use off-the-shelf clustering methods to cluster such data where each image may belong to multiple different semantic classes. Instead, our goal is to cluster pixels across images into semantic classes. Thus, given a completely unlabeled dataset of images, we wish to assign a cluster label to each pixel. This can be thought of as an unsupervised semantic segmentation. A key challenge in performing such clustering is getting an appropriate feature representation, which is difficult without labels. One approach to clustering images, Deep Cluster, learns a cluster-friendly embedding in an unsupervised manner by iterating between clustering, pseudo-labeling, and training. A straightforward algorithm for unsupervised semantic segmentation is to adapt this approach to use pixel-level feature vectors instead of image-level features. However, every iteration, Deep Cluster reinitializes a linear classifier from scratch because cluster assignments in each iteration are arbitrary. This leads to highly unstable training with noisy gradients. Hence, we replace the linear classifier with a non-parametric nearest prototype-based classifier. That is, we cluster the pixel-level features through the entire dataset and obtain a set of cluster centers as well as cluster assignments. Then, we use the negative of the distance between pixel features and cluster centers as class logits and train the network to maximize the probability of the assigned cluster. This encourages the network to embed pixels closer to the center of their assigned clusters and farther from other centers without any need of parametric classifier. The network alternates between these two steps. We now no longer suffer from noisy gradients, and the training objective more closely matches the clustering objective mathematically. However, without any semantically meaningful inductive bias, this approach might learn degenerate solutions such as clustering based on color. To avoid this, we propose to incorporate the inductive bias that the semantic grouping of pixels should have invariance to photometric transformations and equivariance to geometric transformations, i.e., the labeling should not change if the pixel colors are jittered or be worked accordingly when the image is worked. We learn this invariance and equivariance via multi-view clustering, which comprises producing two views per image, clustering each view, and cross-view training. Let's look at the multi-view framework in more detail. First, an image is transformed into two different versions, fed into a shared network, and with L2 normalization, we obtain two sets of pixel-level features. For each view, two randomly sampled photometric transformations are applied, and one geometric transformation is applied on the image and on the final feature maps before and after feeding into the network. The two views that we have for each image can be thought of as forming two views for entire dataset. We perform clustering on each view independently to obtain two sets of centers and two sets of clustering assignments. The network is trained with the two sets of pseudo-labels using the non-parametric classifier described previously. The training objective consists of two terms. The first term, L within, encourages pixel feature vectors in each view to match the cluster labels obtained from that view. The second term, L cross, encourages pixel feature vectors from one view to agree with cluster assignments obtained from the other view. This forces the feature representation to be invariant to photometric transformations and equivariant to geometric transformations. Here we show some qualitative results on COCO and cityscapes. As you can see, PiCIE dramatically improves segmentation especially for foreground pixels compared to both baseline, which is modified deep cluster, and the state-of-the-art. And here are some quantitative results on COCO Stop 15, a popular unsupervised image segmentation benchmark. We find that PiCIE outperforms the state-of-the-art numbers. Here we break down the quantitative result of PiCIE and show that each component contributes to performance substantially. We also show that the learned representation of PiCIE is better for transfer learning and can be used as an initialization for standard supervised training compared to random initialization and the baseline. Finally, we visualize the nearest neighbors of some core pixels from PiCIE. As you can see, all the nearest neighbors are semantically consistent despite that there has been no labels during training. Thank you for your interest in our work, and please check out the full paper for more details and visit our GitHub page for the code base. Thank you.